Okay, so let us start with class. So today, chapter 12, heat conductions and thermal expansion. As you can see here, there are two main subtopics in this chapter. The first one obviously is heat conduction. We are going to see how heat flow in an object, okay, including in metals and an insulator. How it works, how does it move, and what is energy and what is heat energy and what is temperature. And the second thing in this chapter is thermal expansion. So what happens if you heat something up? Of course, it will expand. So we will see how it expands in this case. So 12.1, heat conduction. Heat is defined as energy now. Heat is just a form of energy that is transferred from one body to another body because of the difference in temperature. And usually it's being transferred from a hot region towards a cold region. So if you look at this definition, heat it's just an energy. Okay, it doesn't tell you whether something is hot or is cold. You can feel the hotness or the coolness of something. That is because of the temperature. So if you are just looking at heat itself, okay, you won't be able to tell whether something is hot or cold. You need temperature. So that is the main difference between heat and temperature. Okay, so since heat is a form of energy, the unit is joule. Okay, that is the SI units for energy. So don't get confused. Heat, it won't tell you whether something is hot or cold, the degree of hotness. It won't tell you anything about that. That is the temperature. Okay, the reasons why you know something is hot, because it has a high temperature. The reasons why you know something is cold, that is because of the low temperature. Okay, so thermal conduction is defined as a process where heat is transferred through a solid from a regions of high temperature to a regions of low temperature. Now, if you look at this statement itself, what does it mean? From a regions of high temperature to a regions of low temperature. So it tells you the initial position is high temperature, and the final point, the final destination is a lower temperature end. So that is the part that you need to know, because in equations, you need to take note where is your initial positions and where is your final position. By just looking at the definition itself, it tells you the initial position is a place with a higher temperature, whereas the final position, the final destination, is a part with lower temperature. So if you look at this table, it shows you how heat is being transferred in a metal rod and in an insulator rod. Okay, insulator means it is a non-metal. Oops. Non-metal means there's no free electron inside it. So consider a non-metal rod is being heated at one end as shown in the figure. So you start from end A. Okay, so this end A, we will call it as a hot end. Why? Because it is in direct contact with the heat, with the source. So now you put a fire right here. So now point A is being acted as a hot end. So at the hot end, molecules of the rod, they are receiving heat directly from the fire. So it has a higher temperature right now. So this causes the molecules to vibrate faster and faster. So inside insulator rod, there's no free electron. What we have is just molecule. Okay, so when you heat it up, this molecule, they will move. What is happening is that they are just vibrating. Okay, they were just vibrating, and when they receive more and more heat, means they receive more and more energy. So heat energy is being transferred into kinetic energy. Therefore, they can vibrate faster and faster. So collisions between these hot molecules with the neighboring colder molecules result in the transfer of energy. So energy is being transferred by vibration, okay, to the colder end. So they vibrate, they transfer energy, transfer. Eventually, the energy will reach the cold end. So this transfer of energy will continue until the cold end of the rod becomes hot. And they will stop once point A and point B, they are in a equilibrium state. Okay, it means that the heat flow is at a constant rate. So in a metal rod, what happens? Now, in metal rod, there is a slight difference than an insulator rod. In metal rod, we have a lot of free electrons. So what is the main difference then? What is the difference between electrons and molecule? Now, electrons, they can move freely. Okay, they can move freely inside a rod. So when one end of the metal rod is heated, the free electron will gain energy as well due to heating. As a result, they move faster than before, and some of them, they collide with the colder molecules at point B. So other than the collisions between molecule, they also collides between the electrons and also molecule. Okay, and because electron can move freely, okay, therefore they can reach cold-end faster compared to the vibrations in insulator rod. So this collision causes the cold end of the metal's rod becomes hot, and the transfer of energy by free electron is found to be faster. Okay, it's found to be faster compared to the transfer of energy by vibrating molecule in the lattice. This is because electrons, they are lighter and they can move faster. That is the main thing. Okay, main keywords. So metal move faster conducted the heat compared to the insulator. Okay, so a free electron is the cause, is a factor why you can hit the metals up much faster than an insulator. All right. So now we want to calculate how fast can it flow. Okay, now you heat up the yes.
Madam.
Yep.
Lattice tu apa dia?
Lattice itu
Lattice,
dia macam
lattice.
ya. Lattice itu dia macam dia form dengan yang kemas punya di dalam kita punya.
Lattice tu apa dia? Yang tadi ada atas tu.
Yalah, kamu dengar tak suara saya?
Line dia lambat ni.
Dengar.
Oh, dia lambat. Okay, dia lambat sebab internet. Saatnya I tengok internet connect ke mana. Okay. So internet dia lambat sikit, so tak apa. So lattice itu dia macam susunan kita punya molekul. Okay, di dalam kita punya solid. So kalau kamu nak heat transfer melalui molekul ini sahaja, okay, dia vibrate tapi dia tak akan gerak, dia tak akan move freely. So lattice dia memang susun dengan cantik. So bila kamu tengok satu solid, actually you're looking at in the form of molecule. Okay, so dia bentuk macam begini. So penuh dengan molecule. So dia cuma vibrations. So vibrations inside this, ini kita panggil lattice lah. Boleh faham tak kalau begini? Ini memang lambat sangat dah ini. Hello, dengar tak?
Boleh.
Okay, so lattice ini dia macam susunan molekul kita di dalam satu solid atau sesuatu yang liquid dan sebagainya. Okay, so basically they just shows you this thing lah. Okay, if you're looking at the lattice in physics, basically they just show you this. So the vibrations inside this setup, okay, dia memang dalam form of a molecule. So, okay, now let's look at the rate of heat flow. Okay, let's look at the rate of heat flow. So, okay kan? Memang lambat lah ini.
Okay, dia betul.
Okay, so rate of heat flow. Considering the heat flows through a uniform cylinders as shown in the figure below. So now the heat is flowing from a hotter end to a cooler end. Now, you want to see how fast it can flow. Okay, and that is the reasons why we want to calculate dq over dt. So whenever you want to calculate the rate of something, okay, so this is the method. You divide by the times taken. So the times taken for the heat transfer, you use q divided by the times taken, then that is the rate. So heat conductions between areas at the temperature T1 and T2, figure shows the heat conductions. So area again is the cross-sectional area. Okay, it is not the area of the whole item, but you're just looking at the cross-sectional area of two objects, of two ends. So if T1 is greater than T2, then heat flows to the right. So your T1 in this diagram is larger than T2, which means T1 is a hotter end. Okay, it's a hotter end, and T2 is a cooler end. So in other words, you can say T1 is the initial position, whereas T2 is the final position. So in calculation, you're going to treat T2 as a final and T1 as the initial. So it is found experimentally that the rate of heat flow is given by the relation dq over dt equals to negative ka dt over dx. So this is the equation. Where dq over dt represents the rate of heat flow, A is the cross-sectional area, the area that is joining the two ends. Okay, that is in between the two ends. But you're not looking at the area of the whole rod. That is the things that you have to remember. Okay, that is a very common sense misconception in the exam. When it comes to area, students tend to calculate the area of the whole object. So that is wrong. Okay, remember you're just looking at the cross-sectional area. So temperature gradient is a dt over dx. We will look at it after this one. And then the thermal conductivity. Thermal conductivity is a constant value, okay? It's a constant value which tells you the rate of heat flow per unit area, per unit cross-sectional area. So now what does it mean by the negative sign in the equation? So these equations, you have a negative Ka dt over dx. Every single variables, they carries a meanings, they represent something. Okay, so the negative sign right here, it indicates the flow, the heat flow is always in the directions of decreasing temperature. Okay, so that is what it means by from high temperature to low temperature. Okay, to a lower temperature. That's why we have a negative sign right here. So when you apply these equations, okay, when you apply this equation, what are you going to do right here? These equations actually can be expanded. Okay, becomes negative Ka T final minus T initial over dx, the change in the length of the road. Okay, so you have T final minus T initial. So if you remember that I told you just now, T final and T initial is the hotter end, and T final is a cooler end. Okay, so when you use T final minus T initial, it will give you a negative value. So negative value will cancel with the negative sign in the equation. Therefore, your final answer, your dq over dt, it must be a positive value. All right, because of the negative sign. Okay, because the negative sign, they cancel already. Okay, they have gone. So negative sign in the equations and the negative signs from a dt, they cancel with each other. So your dq over dt, it is a positive value. All right, so don't make mistake in this part. Okay, this is where students always got it wrong. Why? Because of revision books. What happened in revision books? Revision books, they always tell students to use larger value minus the smaller value. That is well, I would say that is a shortcut. I wouldn't say that is wrong. That is a shortcut. Why? Because if you notice, in most of the revision books, the way they write the equation is just dq over dt equals to Ka delta T over delta X. That is from revision books. The reasons why they didn't put a negative sign right here, it is because they already included in the delta T. That's why the delta T in your revision books, they use T large minus T small. Okay, but in terms of concept, this is actually wrong. Why? Because you need the negative sign in the equations, because it shows you the directions of heat flow. Okay, so this, I wouldn't say it's wrong, it's just a shortcut, but you shouldn't use it. Okay, you shouldn't use it. You stick to the original equations that is coming from the definition, that is coming from the experiment. Okay, so this equation is found from experiment. They form from experiment. They conduct a series of experiments, and then they form this equation. So must come with a negative sign. And this negative sign will be cancelled eventually because the dt, you use small t minus a large t. Okay, minus a higher temperature. Right? So if you look at the revision books, you will have different equations. Okay, because they use shortcut. Okay, because they use shortcut. It doesn't mean that they are wrong. Okay, it's just a shortcut. But I would suggest you to stick to these original equations because this is the right equation. This is the correct equations. So the rate of heat flow, again, is a scalar quantity. Okay, because the time is a scalar quantity and also your Q is also a scalar quantity. Therefore, dq over dt is a scalar quantity. So the SI unit is a joule per second or a watt. Okay, watt. So dq over dt, Q we know is energy, so it's joule, T is a time. Therefore the unit, the SI unit is joule per second. Thermal conductivity is defined as the rate of heat flow perpendicularly through the cross-sectional area of a solid per unit temperature gradients along the directions of heat flow. So mathematically, you just rearrange the equation above. Then that would be the definition for thermal conductivity. So dq over dt divided by a dt over dx. Okay, a dt over dx. So that is the equation. You just rearrange the equations of a rate of heat flow. So the thermal conductivity, it depends on the material. Okay, so now you have one variables that depends on material, which tells you the rate of heat flow is actually depends on material as well. Okay, material will affect the rate. So substances that are good conductor have a large thermal conductivity, whereas good insulator have low conductivity. So sometimes the questions will ask you to justify which one is a better conductor. Then what should you do? You compare the values of K. Okay, you compare the K of two given object. Maybe it tells you object 1, metal 1, and metal 2. Okay, then it asks you which metal is a better conductor. Then how are you going to justify your answer? How are you going to tell which one is a better conductor? You can check its thermal conductivity. All right, you check the values of K, you calculate the K for metal 1, you calculate the K for metal 2, and then you compare the value. So the one with a larger value is a better conductor compared to the one with a lower K, a smaller K. So table shows the values of the thermal conductivity for various substance. So this is just a few examples. You don't have to memorize it. Okay, it will be given in the exam. So silver has the highest K, as the largest K, so means it is the best conductor amongst the 5 given examples here. Whereas wood, if you look at the values, is just 0.08. So wood is not a good conductor, obviously, right? When it compares to the silver, to the metals. So factors that affect the heat flow, of course, if you look at the equation itself, dq over dt equals to negative Ka dt over dx. So based on these equations, you can already tell what is the factors that affects the rate of heat flow. First thing is the A. So dq over dt is directly proportional to A. If the object has a larger cross-sectional area, not the whole surface area, yeah, just the cross-sectional area. So let's say now if you have something that looks like this, a rectangular shape, okay, a rectangular shape object, and then so you have a road, and then you heat up the object, okay, you heat them up. So assuming all the other items, okay, all the other quantity, they are the same, they have the same value. So which one will have a faster, a larger rate, okay, a greater rate? Of course, it's the one with a larger cross-sectional area. So the cross-sectional area for object 1, I'm going to call it object 1, and this is my object 2. Okay, so the cross-sectional area for object 1, now the initial position is a place with the heat, with the fire. So this is the initial positions, the bottoms of this metal plate, and then the upper part of this metal plate is the final position. So therefore, the cross-sectional area is this whole surface area. Okay, it's this surface area, excluding the side. Okay, not including the side. So now this one, obviously, it has a larger cross-sectional area compared to the road. The cross-sectional area of the road, now the fire is located here. This is your initial position. The other end is the final position. You look at the positions of fire. The positions of fire, it indicates the initial positions, and the place, the part that is opposite to the fire, then that one we call final position. So final positions for object 2, okay, is the other end of the road, and the cross-sectional area just here is very small compared to this metal plate. So obviously, when you compare object 1 and object 2, object 1 would have a better rate of heat flow. Okay, a better rate of heat flow, a faster rate compared to object 2 because of the cross-sectional area. Providing if dt over dx and k, they are the same. Okay, so that is a cross-sectional area. The second factor, okay, the second factor is the temperature gradient, dt over dx. So according to the equations given, dq over dt is also directly proportional to the dt over dx. So rate of heat flow through substance is proportional to the difference in temperature between its end, and the rate of heat flow also depends on the size and the shape of the object. Okay, so dt over dx, so dx is the length. Okay, dx is the length, and then dt is the change in temperature. And then the last one is the types of material, which is your K. Okay, different material has different K. If you are given 2 different objects, but they are both made by the same material, then they will have the same K, regardless of the shape, okay, regardless of the initial and the final temperature. As long as they are made from the same material, then they have same K. So temperature gradient, what is a temperature gradient? Temperature gradient is defined as the temperature difference per unit length, dT over dx. The units of temperature gradient is a Kelvin per meter or degrees Cm -1. So there are two different cases that we're going to look at. The first one, if when you have insulated material, okay, and then the second one is when you have a non-insulated material. Now, what does it mean by insulated? You put an insulator outside the metal, okay, outside your rod, for example. So there's an insulator on both ends, okay, outside the object. So you wrap it with an insulator. So consider a long uniform conductor, which is thermally insulated as shown in the figure. Since the rod is insulated, there will be no heat flow to the surroundings along the bar. In other words, you can say there's no heat loss. Okay, no loss of energy, no energy loss. Therefore, okay, at a steady state condition, so steady state condition, it means now the heat flow is constant. Okay, the rate of heat flows through the conductor is constant. So it doesn't matter which part of the rod that you're looking at, every part of it, okay, for example, if you look at this part, okay, you look at point A, you look at point B, and then you look at point C, okay, you look at point C. All of them, they have same dq over dt because now the rate of heat flow is constant when the object is reach a steady state, when it is at steady state condition. So you will see this term very often in your questions, okay, because it tells you now the rate of heat flow in every part along the road, they are constant, they are the same. So sometimes you will have a questions where you have two joining rod, they are joining together. So this is material A, this is material B. But if the question say now these two rods, they have reached a steady conditions, steady state, it means the rate of heat flow in the rod A is equal to the rate of heat flow in rod B. All right, they are equal. That is the meanings of steady state in your questions. So at a steady state, the rate of heat flow through the conductor is constant. In this condition, the temperature gradient will be constant along the bar. Okay, so when you plot the graph of T against X, you obtain a straight line, okay, a straight line graph. The rate of heat flow through the rod can be written as dq over dt equals to negative Ka T2 minus T1 over L. So if you look at this graph, okay, at the beginning of the road, this is 0, and at the end of the road, at the end of y, okay, at the T2, this is the length x. So starting from 0 positions, the 0 cm, the initial position, it has the highest temperature according to the graph. All right, why? Because now you put a fire here. This is the end that you put it close to the fire, okay, where you place the fire beside it. So now you put it, you put a fire here, therefore your initial position is start from the highest temperature. So as it gets further away from the x, okay, if you look at here, this is x, this is y. As it gets further away from x, the temperature decreases, okay, because now the temperature just start to flow from T1 towards T2, from x towards y. So the temperature is decreasing as it gets further away from the fire. So this is your fire, right? So it gets further away from the fire, the temperature is lower. But now the heat flow is at a constant rate, okay? So the heat is flowing in a constant rate, but it doesn't mean that the rod, okay, the rod have the same temperature at every position. Just the rate of heat flow is constant, okay? They still have different temperature, all right? So don't get confused, yeah? Don't get confused. At steady state, only dq over dt is constant, right? T is not constant. So jangan ingat bila di steady state T pun sama, tidak, okay? T tak sama, cuma rate untuk energy flow sama. Okay, energy flow di sepanjang bar ini is flowing at the same rate. Now, what happens in a non-insulated material then? For a non-insulated conductor, heat can escape from side. So it means heat is lost, okay? That this road, it experiences energy loss to the surrounding. Therefore, the rate of heat flow decreases as the distance increases from x, okay? As it gets further away from the heat, from the source of the fire. So the temperature gradient also decreases as the distance increases. Why? So try to imagine if you have an insulated rod, okay, if you have an insulated rod, now I'm going to draw it on the right hand side. So if you have an insulated rod at position, okay, now this is being insulated. Okay, it has an insulator around it. So insulated metal rod. Okay, so since there's no heat flow, let's say now this is a position, let's say this is a 1 cm positions, 2 cm, 3 cm, and then this is a 4 cm. So let's say you start from here, okay, this is the hot end. It starts from 50 degree. Okay, so at 1 cm, positions 1 cm, now it decreased to 40 degree. But because there's no heat loss, so for every 1 cm, the temperature will decrease by 10 degree. Okay, because it's flowing at a constant rate, okay, constant speed throughout the whole metal rod. So for every 1 cm, the temperature will decrease by 10 degree. Okay, but what happens right here when you have a non-insulated material? Okay, when you have non-insulated material. So now you still have 1 cm position, 2 cm position, 3 cm, and 4 cm. So again, you start from here, the hot end. Let us begin from 50 degree. So when it reaches 1 cm, now maybe now you just have a 30 degree here. Why? Because some of the heat, some of the energy is being transferred to the molecule outside the rod. Okay, outside the rod. So it's being transferred to the air molecule outside it. So you can feel the heat around the metal rod. Okay, so some of the heat is being transferred. Therefore, the temperature decreased. Okay, the temperature decreased much faster compared to the one above. Now it's 30 degrees. So for another 1 cm, maybe now the temperature loss is 10 degrees. Why? Because now you have less energy. Okay, you have less energy compared to 50 degrees. So less energy means also less energy loss during this 1 cm length. Okay, so less energy is lost right now. Therefore, it just decreased by 10 degrees compared to just now 20 degrees. For another 1 cm, maybe now the temperature is 15 degrees. Okay, so it's not at a constant rate. Okay, it's keep decreasing. It decreases exponentially, as shown in the diagram here. Okay, the rate of heat flow it decreased. Why? Because now you have less and less energy inside the rod. So when you have less and less energy inside the rod, definitely the rate of energy loss also decrease. Okay, the rate of energy loss also decrease. So that is the difference between insulated material and non-insulated material. For non-insulated material, heat is lost to surrounding because the vibration is not just occurring inside the rod itself, but it's also with the air molecule around the metal rod, okay, at the surrounding. So when you have the
For the insulated material part,
Yes.
would the other end, cooler end, eventually reach the same temperature as the hotter end if we
Yes,
continue heating it?
Yes, it should.
Okay. Thanks, Madam.
Right. Okay. But in our syllabus, we will assume the temperature is never different because we will just look at one moment. Okay, we're not looking at when the temperature at the colder end is equal to the temperature at the hotter end. That one will take quite a bit of time. Okay, so usually what we do, we'll just look at one moment. Okay, we take moments where temperature from a cold end to a hot end, they have a fixed rate. Okay, they have a fixed value. That's it. Okay, we're not looking at when we're not looking at when both ends they reach the same temperature. But of course, in reality, if you keep heat it up, then eventually both ends they will have the same temperature. So the combinations of the rod in a series. So in our questions, okay, sometimes you will have two rods joining together with a different material. Okay, and then you put an insulator around it. So what happens right here now? You look at the graph. You have two different straight lines. Okay, two straight lines with different gradient. Why? Because different materials they will have a different temperature gradient. You look at this dt over x. Okay, and also because of the different materials, they come with different k. Okay, and if you look at the definitions of k again, okay, we go back to the definitions for k. If you look at this definition, okay, you look at this equation, it shows you k is inversely proportional to dt over dx, which means if you have a good conductor, then the dt over dx, the temperature gradient, is smaller. Okay, it has smaller value compared to the poor conductor. So if you look at this diagram, according to this diagram, now you have a hotter end, which is T1, the one with the largest temperature. This is where you put a fire, the source of a fire. So now you heat it up from a T1. Okay, so T1 has the highest temperature, and then you have a T3 here, which is the part that is joining both materials. And then you have a T2 at the other cooler end. Okay, so this is a hotter end, and then this is the cooler end. And T is the point that is joining materials C and D together. So if the question tells you now the object, these two rows, they have already reached a steady state, then we can say the rate of heat flow through both material, they are the same. Okay, therefore we have dq over dt C is equals to dq over dt D. So they have same rate. Okay, they have same rate. The difference in the equation, now if you expand the equation, what are you going to get? Since we know dq over dt is equals to negative ka dt over dx, all right, dt over dx. If you expand the equations, you will obtain negative kc. Okay, but the a would be the same. Why? Because now you join them, and the two of them, they are touching. Okay, they have the same cross-sectional area. The place that where they touch each other, they have the same cross-sectional area. Therefore, negative kc a, and then you put a bracket here. So T, dt, you want to look at T final and T initial. So you have to be extra careful. When it comes to material C, T final is actually T3, not T2. So T3 minus T1 divided by the X for C. Okay, and then equals to negative K. Now, since you're looking at material D right now, so KD, A, so same cross-sectional area. Okay, and then for the temperature, now you look at the beginnings of material D. So it starts from T3. Therefore, T3 is acting as the initial position for material D. Okay, just now T3 is the final position for material C. But right now, it is acting as the initial position for material D. So you will have T2 minus T3 for material D. Okay, over XD. So you can actually simplify the equations, okay, by removing the negative sign and the A from the equation. So this is how you solve the questions when you have the combinations of roots in series, right? So yeah, this is how you apply these equations if the object is in steady state. So from the equations of thermal conductivity, like I told you just now, K is inversely proportional to dt over dx. So if you have a Kc larger than Kd, means Kc is a better conductor, then dt over dx for C is smaller than dt over dx for X. Therefore, if you look at this graph, for material C, the gradient is less steep compared to material D is steeper. Okay, so ini gradient dia lebih besar. Okay, higher gradient, larger gradient. And then this one with a smaller gradient. Okay, smaller gradient, less steep. Why? That is because of the values of K. So you can roughly know the shape of the graph by looking at the values of K. So if you're given two different material and the question asks you to sketch a graph, you check the values of K. From there, you will know the shape. Okay, you will know how to sketch the graph for temperature against X. Okay, for T against X graph. So temperature gradient in a material C is smaller than the temperature gradient in material D, okay, because of Kc is larger than Kd. So this is the relationship that you need to know. Kc larger than Kd, therefore dt over dx for C is smaller than dt over dx for D. Okay, so sometimes question will just ask you to sketch without giving you any value. So how do you know the shape? You know the shape by looking at the constant value K. All right. So we are done with the thermal conductions. Now let's look at the thermal expansion. Thermal expansion is much easier compared to thermal conduction. Why? Because you just have one equations, but you apply it for three different scenarios, three different cases. So define the coefficients of a linear area and volume thermal expansion. Three types of expansion, but their equation looks similar. So thermal expansion is defined as a change in dimension. okay, change in dimension, because now it expands of a body accompanying a change in temperature. So you change the temperature, and as consequence, the dimension changes as well. So the thermal expansions of an object is a consequence. Yeah, this is what I told you just now. It's a consequence of the change in the average separations between its constituent atoms and molecules. So at ordinary temperature, molecules vibrate with a smaller amplitude. As temperature increases, the amplitude increases because it receives more energy from the heat, from the source, from the fire. So this causes the object as a whole to expand. So there are three types of expansion: linear, area, and volume. So first, consider a thin rod of initial length at the temperature T0 initial is heated to a new uniform temperature. So now this is what you asked me just now. If you heat up the object, will they have the same temperature at both ends? Yes. Okay, so when you have the same temperature at both ends, then now we have a case of expansion. All right, so this is when you heat up the object until the whole thing, they have a uniform temperature inside it. So consider a thin rod of initial length at the temperature T0 is heated to a new uniform temperature. So what happens right here, if you look at this diagram, so the length becomes longer, they expand. Okay, they expand. Why? Because now molecule inside is vibrate. So the amount of molecule is still the same, okay, but now they vibrate with a larger amplitude. Okay, they vibrate with a larger amplitude, and therefore the length increased. So you look at this diagram, it seems like it increased a lot, right? But actually this diagram is a bit misleading. Okay, in reality, the increasing in length maybe it's just 0.001 mm, something like that. Just a very, very small. Okay, delta L usually is just a very small value. So this diagram, okay, the reasons why they show you like this, so that you can see it. Okay, you can see it, but it doesn't mean that they increase that much. It is impossible for something to increase that much, okay, to expand that much. So it is found experimentally that, okay, the change in the length is directly proportional to the change in temperature. So obviously, okay, if you increase the temperature, the molecule will vibrate at a larger amplitude, therefore it expands more compared to the lower temperature. So this is the first thing that the scientists found in that experiment. And the second thing that they found, if you have a longer initial length, okay, as for the same temperature increase, so 4-meter long iron rod will increase in the length twice as much as the 2-meter long iron rod. Okay, so the change in the length is directly proportional to the original length. So this these are the findings from the experiment. Okay, so the scientists, they conduct a series of experiments, and then they came into the conclusions. Okay, they found out delta L is directly proportional to delta T, and then delta L is directly proportional to the original length. So when you combine these two relationships together, you will obtain a new relationship called delta L is directly proportional to del T L naught. Okay, but this one, you cannot change it into an equation yet. You cannot use it in a calculation. It just shows you the relationship. Okay, this sign, it just gives you the relationship, whether they are directly proportional or they are inversely proportional. So to make it into an equation that can be used in our calculation, we give it a constant. Okay, we add a constant into this relationship. Therefore, you obtain an equation delta L is equals to alpha L naught delta T. Okay, L naught delta T. Or it can also be written as alpha L naught and then your T final minus T initial. Right? Now, when we talk about T final minus T initial, of course, you can have negative value. Why? Because sometimes you will cool down an object. Okay, sometimes the objects cool down, then the length will become shorter. They will contract. Okay, rather than expand. So in that case, if you have a decrease in temperature, then your delta L would be a negative value. Okay, kalau temperature decrease, kamu punya delta L pun akan decrease sebab dia sekarang mengecut. Okay, mengecut. So you can have a positive value, you can have a negative value. It depends on whether it expands or not. Right? So delta L means the change in temperature, L final minus L initial. Delta T change in temperature, final T minus initial T. And alpha is the coefficient of linear expansion. Okay, this is the coefficient of linear expansion. So we will have three different coefficients, one for linear, one for volume, and one for area. So right now we are looking at linear expansion. So if you rearrange the equations, then the definition for coefficients of linear expansion is alpha is equals to del L over L naught del T. So basically you just have one equation, but then you rearrange it. Okay, you're just playing around with the equation, rearrange it to get a different definition. So coefficients of linear expansion is defined as a fractional increase in length of a solid per unit rise in temperature. So the equations now, other than delta L equals to alpha L naught delta T. Now what I want to do, okay, I want to expand the equation. Since delta L is equals to L minus L naught, now if I expand the equations, I have L naught on both sides, right? I have L naught on both sides. So I move L naught to the right hand side of the equation, and then I factorize it out. Okay, so therefore the equations, the final length can be calculated by using L equals to L naught bracket 1 plus alpha delta T. Okay, 1 plus alpha delta T. So the original equation that is coming from the experiment is for delta L, the change in length. If you expand these equations, then you'll be able to calculate the final equations by the final length by using L equals to L naught bracket 1 plus alpha delta T. Okay, but actually they are all coming from the same equations. You can also use the equations above to solve it. Okay, you can also use the equations delta L equals to alpha L naught delta T to solve it. That is fine, as long as you understand what does it mean by delta L. So delta L, it means L final minus L initial. Alright. So semua dia actually dari equations yang sama. Okay, cuma tengok macam mana anda main dengan equation sahaja. Okay, so notes. So this is what I told you just now. If the change in temperature is negative, means something you cool down something. Okay, something is being cooled down. Then delta L is also negative. Okay, therefore it means the length decreases. So the temperature change is the same in Kelvin and Celsius scale. Therefore, it doesn't matter, okay, whether you use K, Kelvin, or degree C for delta T, okay, because the value is the same. But when it comes to chapter 14, okay, if you're just looking at temperature, not the change in temperature, not the temperature change, then you must use Kelvin in your calculation, because Kelvin is SI unit. Okay, and degree C is not SI unit. But if you're looking at temperature change, okay, delta T, then delta T in K and delta T in degree C, they are the same. All right, so in chapter, this is chapter 12. In chapter 12, it doesn't matter whether you want to use degree C or you want to use Kelvin, right? So kena ingat ya, yang ini cuma valid untuk change in temperature. So change in temperature 1K sama dengan 1C. Okay, kalau kita kata change in temperature. Tapi kalau kamu tengok temperature sahaja, okay, if you're just looking at the temperature itself, then 1K is not equals to 1 degree C. All right? So you have to remember, they are different if you're just looking at temperature or temperature change. So the unit for alpha is either degree C -1 or K -1, depends on the unit for your delta T. Okay, kalau delta T, K, then alpha K -1. If delta T is degree C, then alpha is a degree C -1. So L could be the length of the rod and the side of a square plate or a diameter of a hole or radius of the hole. Okay, anything. The L could be anything. So note that the linear expansion has no meaning for a liquid and a gas, since they do not have fixed shape. So when it comes to expansion, okay, for linear expansions, we just look at solid. Okay, because the liquid and the gases, they don't have a fixed shapes. So L, it could be the length, okay, it could be the side. So this one, even though if you look at it as a whole, it is area for the second diagram. Okay, this is 1, this is 2, this is 3. So you look at 1, definitely is a length, but if come to object 2, okay, if it comes to a diagram number 2, now this one, you can solve it by using area expansions or linear expansion. If you want to solve it by using linear expansion, then you just look at one side. Okay, you just look at one side. You don't look at this object as a whole. All right, you don't look at it as a area. You just look at the side. So for this circle, if you don't want to solve it as an area, then you look at the radius. Okay, the length of the radius or the length of the diameter. So you look at the length. So you can solve area by using linear expansion method, but then you have to be careful, okay, which value to be used in your calculations. All right. So done, that is linear expansion. Now area expansion. So area expansions, this type of expansion involve the expansions of the surface area. So just now for object number 2, you just look at the length of the area, the side of the area. Now this one, you look at it as a whole. Therefore, you have an area right now, okay, rather than side. So consider a plate with initial area A0 at temperature T0 is heated to a new uniform temperature and expands by delta A as shown in figure. Okay, so it is found experimentally. So again, you obtain the same relationship. Okay, scientists, they found that delta A is directly proportional to delta T, and delta A is also directly proportional to A0. So when they combine these two relationships, they obtain a new relationship. Delta A is proportional to A0 delta T. And again, you want to change it into mathematical equations. Okay, so you add a constant. Okay, you add a constant into the equations. Therefore, delta A is equals to, now, since you want to add a constant, a new constant, we call it beta. Okay, delta A equals to beta A0 delta T. Now you see, the way we form equations, the way we write equation is exactly same as linear expansion. The difference is in the symbols that is being used in the equation. In linear expansion, we use L. In area expansion, we use A. In linear expansion, we use alpha. In area expansion, we use beta. Okay, so delta A, it represents the change in area. Delta T, change in temperature. Beta is the coefficients of area expansion. Okay, so don't get confused. Alpha is not the same as beta. Okay, they are different. So what is the relationship between them then? So coefficients of area expansion is defined as a fractional increase in area of a solid surface area per unit rise in temperature. So again, what are you going to do is to rearrange the equations above. Okay, the equations from the experiment. You rearrange it and then you obtain beta is equals to delta A over A0 delta T. So this is the definitions for beta, coefficients of area expansions. So again, you're just going to repeat the same thing to find out, to derive the equation for final area. So final area is equals to, okay, is equals to what? So it's equals to A0 bracket 1 plus beta delta T. Okay, so you see, again, it is very similar to linear expansion. Linear expansions, we have L equals to L0 1 plus alpha delta T. Area expansions, we have A equals to A0 bracket 1 plus beta delta T. Okay, so the unit for beta same as alpha. Okay, just that you use it for different types of expansion. Okay, volume expansion. Okay, volume expansions, consider a metal cube with a side length L0. So again, now if you want to look at it as a volume expansion, then you don't look at the length. Okay, if you want to look at it as a linear expansion, then you just look at one of the side, one of the length. So consider a metal cube of side length L0 is heated and expands uniformly as shown in figure. So to be more precise, I'm going to call it V0. So you expand it, eventually obtain V final. Okay, initial V, final V. So experimentally, okay, again, scientists, they conduct a lot of experiment and they found that del V again is directly proportional to del T. And del V is also directly proportional to V0. And once again, if you look at these two relationships, you combine them together, you obtain a relationship del V is proportional to V0 del T. Okay, so this is a relationship. If you want to change it into mathematical equations, once again, you add a constant to it. Therefore, you have del V equals to gamma V0 del T. Aha, so if you compare these three equations, del L equals to alpha L naught del T, del A equals to beta A naught del T, and then a del V equals to gamma V naught del T. Isn't they looks very similar to each other? The only difference is in the symbols that you use. Okay, for length you use alpha, for area you use beta, for volume you use gamma, right? But the ways you write the equations, they are exactly the same. So gamma is the coefficient of volume expansion. Okay, so gamma we use it for volume. So coefficients of volume expansion, once again, if you rearrange the equations, then you obtain gamma equals to del V over V naught del T. And once again, the final V can be calculated by using V naught 1 minus gamma del T. So again, if you write down the three equations, you will see that they look very similar. So L final equals to L initial 1 minus alpha del T. V final equals to V initial 1 minus gamma del T. A equals to A initial bracket 1 minus beta del T. So again, you see the equations, they look very similar. Okay, the difference is in symbols used. So thermal expansions of a liquid. So when a liquid is in a vessel, is heated. So both liquid and vessel, they expand in volume. So now you have a container, let's say. Okay, the container. So you place liquid in it. Okay, ada liquid, ngam-ngam penuh. Okay, so full of liquid. Okay, so when you heat it up, what happened? So both of them, they expand at the same time. Okay, the container expand and then the liquid also expand. But the liquid in a solid container, they expand much faster than solid, okay, resulting in the rise in the level of liquid. Therefore, what happened is that now they will overflow. If you heat it up, then the water, the liquid will start to flow out, okay, because it expands much faster compared to the vessels, compared to the container. Therefore, if the question asks you to calculate the overflow amount, you use V liquid, okay, the final V of a liquid, minus the initial V of liquid. Okay, minus the initial V of liquid. So that is how you calculate overflow. All right. So when it comes to liquid and solid, okay, when it comes to liquid and solid, but yeah, let me see. The reasons why it expands faster, that is because, okay, that is because the gamma is larger. Okay, the gamma for liquid is larger than the gamma for solid. Okay, therefore it expands much faster. So it depends on the values of coefficients of volume expansion. The one with a larger coefficients, they will expand much faster compared to the one with a smaller coefficient. Okay, compared to the one with a smaller coefficient. Therefore, it can overflow. So I think in your notes, something is missing. Okay, so I want you to write it down, which is the relationship between alpha, beta, and gamma. All right, so write it down. This is missing. So sometimes questions will just give you the values of alpha. So you have to know beta is equal to 2 times alpha. Okay, and then gamma is equal to 3 times alpha. So this is missing. Okay, this is missing from your notes. Make sure to write it down. Dalam nota kamu, dia tercicir equations ini. Okay, dia terlupa nak tunjuk Anda hubungan antara beta, alpha dengan gamma. So Anda catat. Okay, Anda catat dalam buku Anda. Okay, so done. Okay, that marks the end of chapter 12. We are done with chapter 12. Basically, it's just about the expansions and the conductions of heat. All right. So I think that's all for today. If no questions, then you may leave the class now.
Thank you, madam.
Thank you, madam.